Dear colleagues, it's my sincere pleasure to present our joint research devoted to contact problems for cracks under impact loading. This research has been supported by various funding agencies, and we're very grateful for this support. We all know the structural materials contain different cracks, delaminations, and crack-like defects, and those cracks would significantly decrease the strength of material and may lead to a sudden fracture. It's possible to consider cracks inside the material, inside the layer of material, and cracks being located at the interface. From a mathematical point of view, in the most general case, we may consider two different materials with different properties and a crack located at the interface between those materials. The limiting case, the properties of both materials are the same, and then we have crack being located at homogeneous material. We apply dynamic loading, and in this case, the stress strain may be calculated using the Lemma equations of linear elasticity. We also have initial and boundary conditions. We have no displacements at the initial moment of time, and we have continuity equations for displacements and tractions at the interface. It's also possible to calculate the traction vectors as a crack surface, and at the infinity we would have a finite elastic energy. And we will see how these conditions are satisfied when we solve our problem. So, it's possible to use some linear dynamic identity to represent displacements and the dependence of displacements from tractions. And we also have those two integral kernels here. The first one, kernel U, is the standard one, so it's a green displacement tensor. If we apply the following differential operator to the kernel U, you would obtain kernel W. So it's possible to calculate W. And furthermore, if you apply this differential operator to the Semeliana dynamic identity, you would obtain slightly different representation. So you would be able to calculate tractions everywhere from tractions and displacements at the interface. Kernels K and F may be obtained from kernel W using the same differential operator. And if you go for limiting case, if you go to the interface, then you would obtain the following set of integral equations for tractions and displacements. It's different for different types of the loading. If you have harmonic loading, then everything would be harmonic, so represent tractions and displacement harmonic function with appropriate coefficients. And then the system of boundary equations would look like that. I know it looks a little bit scary, but it's possible to solve the system of equations with the appropriate integral kernels. For harmonic loading, we would have function psi and xi being dependent on exponential functions. And the major problem would be the hypersingular, singular, and weakly singular integrals. All types of divergence integrals which must be regularized and calculated. For example, for the case of Galerkin methods, you would have the following integrals to be calculated. It's all doable analytically, and that's a big relief. And it's possible to solve our problem. If you solve the problem, then you would get a solution which would look like something like that. So that's the distribution of normal and tangential tractions at the bonding interface. For the simplicity, in this presentation, we would consider only 2D problems and normal loading of our crack. You can clearly see that the solution significantly decreases with increase in the distance from a crack tip, and that's exactly what we need. So our Sommerfeld condition is satisfied. And now let's think about another problem. The crack faces may interact, and they would always interact if you have dynamic loading. We have no idea about the contact area, and the performance would be highly dependent on the properties of the contacting surfaces. So the problem would be nonlinear, and it's quite tough to solve this problem, and not many research groups are able to solve such types of the problem. In order to take the contact into account, we use the following constraints. So we have signorini constraints for normal components of the solution, which simply means that there is no interpenetration of crack faces. And for tangential components, we have the Coulomb friction law, which means that there is no slipping if the friction force is high. It's possible to represent the solution using the Fourier series, and it's easy to get the model solution, the harmonic solution. We just disregard those coefficients and we forget about this summation. So if k equals just to 1, then it would be standard harmonic solutions dependent on cosine and sine only. But if we use the whole Fourier series, then you would get non-harmonic solution. So it would be cyclic, but not harmonic anymore. And the solutions hopefully would be physical. So we would have no interpenetrations, we would have frictions as the crack surfaces, and stress strain distributions would be different from the one obtained using the harmonic approach. In order to do it, we use constrained iterative algorithm. So we solve the solution we solve the problem step by step, slightly correcting the solutions at every step. And at the very end, we must have a physical solution which would not need any correction anymore. This algorithm may be called Udzawa iterative algorithm. And that's how the corrected solution looks like. It's a crack surface. It's linear crack under normal tension compression. The gray surface is displacement jump. You can see it's only positive, which means that crack may be only opened or closed. And where crack is closed, we have this white surface, and that's contact forces at the crack surfaces arising only in the area of actual contact. And the most important from a point of fracture mechanics, stress intensity factor. We have two different solutions. One obtained disregarding contact interaction, that's the red line, and black circles. And we have a blue line. This one is obtained taking the contact into account. We can clearly see a huge difference in magnitudes, and we can clearly see a huge difference at frequencies for those maximums. So we can see that the difference would be up to 50%, which is quite high. So that's homogeneous material under tension compression loading, taking the contact interaction into account. It's possible to solve the problem for different angles of incidence, and you would see the appropriate difference between solutions. It's up to 50%, as we discussed before. Now, for interface crack, for example, for crack between steel and aluminum materials, you would have a very similar distributions of stress intensity factors. Huge difference in maximums and the appropriate difference in frequencies. That's the solution for normal opening mode, and we have a similar picture for shear mode, depending obviously on the appropriate friction coefficient. It's possible to analyze the convergence of the solution with respect to different iterative coefficients in Udzawa algorithm. Generally speaking, the high iterative coefficient is the faster our algorithm would converge. But for some iterative coefficient values, it would be no convergence at all, like here. And that means that it's quite difficult to find the appropriate coefficients. So we need to think about the appropriate iterative coefficients every time we solve the problem for different types of the loading and different frequencies. It's also possible to analyze the convergence with respect to iterative coefficients, and we can see this convergence. And it's possible to analyze the convergence with respect to the quality of the space approximation. A number of Fourier coefficients involved in the solution process. So we start from 2, 3, 4, 5, and so on and so on. And here we have higher values of Fourier coefficients, we can clearly see that generally it's enough to have about 10 Fourier coefficients for harmonic loading, and we will see later on that this number is very different comparing to the case of impact loading. Now, what happens if we have impact loading and if we still want to use all techniques developed for harmonic loading for the case of general dynamic loading? That's how a system looks like, just a brief reminder. And that's how integral kernels would look like for the case of harmonic loading, our exponential functions as before. And for impact loading, we have Heaviside functions here. Usually people would consider the following types of stress pulses. We would be mostly interested in Heaviside pulse, that's impact loading, and trapezoidal stress pulse. That's how Heaviside pulse looks like, and that's how trapezoidal stress pulse looks like. And the whole idea is we consider trapezoidal stress pulse, but we make it very steep, like that. In this case, we have a stress pulse which is very close to the Heaviside one. And when we use this pulse, and if we repeat this pulse many times, we may use our previous technique because we may easily approximate the repeating pulse using Fourier coefficients and Fourier series. That's how the comparison between solutions obtained in time domain and frequency domain looks like. So you can clearly see that our solution, a solid line, is extremely close to the solutions obtained by Jank and Wünsche. They're the solutions for trapezoidal pulse. And now we have trapezoidal pulse, which is close to Heaviside, but still not yet Heaviside. And we can see the difference. So we are not there yet. But if we make our pulse even steeper, then we have almost ideal coincidence, which makes that we can easily disregard this part because we need this part only to get a repeated loading, and we just focus on this bit. So it's possible to solve dynamic problem for any type of the loading using solutions obtained for frequency domains. And now what happens if we use the same technique for interface crack? That's the dependence of the solutions on the number of Fourier coefficients. You can see that the number of Fourier coefficients are now much higher than before. Before we needed just 10, and now we need higher values. We decided to stop at 50. That's a solid black line here. That's normal opening mode, and that's shear mode. So 50 is the optimal value according to our research. And that's how stress intensity factors looks like for different types, different combinations of material properties. Steel aluminum, steel epoxy, steel concrete, and steel lead. Normal opening mode and shear mode. And finally, let us consider crack closure, friction, and normal interaction of crack faces. Those are pulses which were considered, but we will focus on the actual Heaviside step loading. That's how the dependence on the solutions on number of iterations looks like. So we can clearly see the convergence for a friction coefficient which is equal to 20% for those iterative coefficients. Same picture for a different friction coefficient, but if we drastically change the iterative coefficient, then our solution as before may have no convergence at all. So we shall be very clever when we use the appropriate iterative coefficients. And if you do it properly, you would get the following dependence of the solutions on the number of iterations. So we can clearly see the convergence as before. And that's the last slide of this presentation. We can see that how our solution depends on the friction coefficient. And we can see that with the increase of friction coefficients, and please remember that we have no idea about the actual friction coefficients inside the cracked material, we have dynamic results being below the static values, which means that we can get a range of possible set intensity factors from a worst case scenario to the best case scenario. So those are main results of our research. Thank you for attention, and I would be quite happy to answer any questions if it would be a live discussion. Thank you.